So in this video, we're going to be looking at electromagnetic induction and Faraday's law and Lenz's law. Before we look at those, we're going to look at magnetic flux. So remember, magnetic flux has this Greek symbol, this one here, psi. So the flux is defined as just the product of the magnetic field strength multiplied by the area perpendicular to the field. So this is the flux, and it's magnetic field strength times by area perpendicular. Now it's measured in standard units of Webers. So the standard unit is Webers. So magnetic field strength has to be in Teslas and area has to be in meters squared, and the standard unit is WB, the Weber. So basically, if you increase the area, then you're going to increase the flux. If you increase the magnetic field strength, you're going to increase the flux. So we talked about electromagnetic induction, and that's just the process whereby if you have a changing magnetic flux, that induces a potential difference in the conductor. So we saw that if you had a loop of wire and you moved a magnet into that, then you were changing the flux through the loop, and then a current was actually induced. And that current was induced because there was a potential difference. And we called that potential difference an electromotive force because that drove the current through the wire. And that EMF has a symbol of EMF. That electromotive force has a symbol of EMF. And that EMF has units of voltage. So there's three ways you can change the flux through a wire or a coil of wires. You can change the magnetic field strength, you can increase or decrease the area, and you can move the conductor faster or slower, because remember that induced EMF is actually equal to the change in flux over time. So as long as you're changing flux, then it's going to induce a current. So you can change a flux by moving it quickly, by changing the magnetic field strength, or changing the area. And so remember, if you move the magnet quickly, it induces a bigger EMF. You move the magnet slower, then it's going to have a smaller EMF. And if we have n conducting loops, well, then it's just going to be n multiplied by the change in flux. So recall that change in flux is actually final flux take initial flux, and you're going to have to calculate that change in flux. So this is actually Faraday's law, which I don't recall. I didn't actually make that clear. So Faraday's law states that the induced EMF is equal to the rate of change of magnetic flux. So the change in flux over time. And then this is Faraday's law for n conducting loops. Now that brings us to Lenz's law. Now I'm going to get you to watch this video as well. You can watch it after this video. It'll be linked on Daymap. So basically this is Lenz's law. So Lenz's law states that the direction of the current created by the induced EMF is such that it opposes the change in magnetic flux that originally produced the EMF. So basically what happens is, if you have, let's jump to here. Oops, I actually wanted the video. It doesn't matter. We can imagine it in our heads. Oh, here. Okay, this is a good picture that I can use. So, if we have a magnet and we move the magnet downwards, we're increasing the flux through this wire. Now, what happens is there is a current that is created inside. So when we move the magnet down, it increases the flux, and that flux induces an EMF and hence a current through this wire. Now, the direction of the current, okay, which is what Lenz's law is, the direction of the current is in such a direction such that its magnetic field opposes the magnetic field that created it in the first place. So the current produces a magnetic field that is equal and opposite to the magnetic field that made it. Because if it created a magnetic field that added in the same direction, well then, basically, energy would be getting created. And basically, Lenz's law on the conservation of energy. So if the second magnetic field, the one that was induced in the wire, acted in the same direction as the first magnetic field, then the two fields would add together and it would cause the current to double, which would produce another magnetic field, which would increase the current, and so on. And this would be creating energy from nothing. And this can't be the case. So therefore, Lenz's law must satisfy the law of conservation of energy. So basically, you need to be able to use this, and I'll show you a couple of examples in a past exam question. And it's basically, Lenz's law states the direction of the current created by the induced EMF is such that it opposes the change in magnetic flux that produced the EMF in the first place. And I'll show you what I mean in this example. So, part A, explain why a current is induced in the loop of wire as a magnet approaches the loop. So I'm just going to talk it through. So why is a current induced in this loop of wire? Well, as this magnet comes closer to the wire, it changes the flux through the wire because the magnet is coming closer. So when there is a change in flux, that change in flux is going to induce an EMF, and hence it's going to induce a current through the wire. Okay, number one. Now, number two, explain the effect that moving the magnet towards the loop with a greater speed will have on the magnitude of the current. So, Faraday's law is that the EMF will be equal to the change in flux over time. Now, if a greater speed, that means we took less time. And if we divide by a smaller number, we're actually going to have a larger EMF. Okay, so moving the magnet faster is going to induce a larger EMF and hence a larger current through the loop. Now, the third one, state and explain using Lenz's law the direction of the induced current through the loop of wire. So we know that the wire, this current running through this loop, it's either going to be in an anti-clockwise direction or a clockwise direction. And these are past exam questions, you working out which direction the current's going to go. Now, the way we're going to do this is the following. We're going to use Lenz's law. Now, this magnet gets moved down into the wire, so the magnetic field is going to increase into the page. So we would actually, if we were like a top-down view, it would be like if we had X's, the X's would actually be getting stronger. The magnetic field would be increasing into the page. Okay? Now, the current, okay, now through the wire, it's either going to be in this direction, in a clockwise direction, or it's going to be in an anti-clockwise direction. Now let's do clockwise first. So if you have the current in a clockwise direction, so do the right-hand rule, your thumb goes in the direction of the arrow, the field lines are going to be going into the page in the middle here. So this is going to be creating a magnetic field into the page. However, then what we're going to get is, if we're increasing the magnetic field into the page, then they're going to be adding. So it's not going to be clockwise. It's going to be anti-clockwise, because if you do the right-hand rule, thumb, the magnetic field is actually going to be coming out of the page. Okay? And we know it has to be out of the page because this magnetic field has to oppose this magnetic field. So when the magnet gets brought down, the magnetic field increases into the page. So obviously the current has to be going in an anti-clockwise direction, because then the field will be becoming out of the page, and then the out of the page will oppose the into the page. And that's what Lenz's law is. Lenz's law states that the direction of the current created by an induced EMF opposes the change of magnetic flux that produced it in the first place. So magnetic flux into the page, or magnetic field into the page, and therefore the current produced in the coil or in the wire must be out of the page. So it's going to be in an anti-clockwise direction. Lenz's law is tricky, and I'll explain it in some past exam questions on Thursday. Some further ones. But I am going to explain it further in a couple more. So here we have a past exam question. So obviously the X's mean the field, magnetic field's into the page. We had a circular conducting loop. We had the area, uniform magnetic field. 2 points on the loop are labeled A and B. The loop's perpendicular to the field. The magnitude of the field was increased uniformly, so from 0.04 Teslas up to 0.12 Teslas. So the magnetic field is increasing into the page, okay? So that change in magnetic flux through the wire is going to induce a EMF and hence a current through the wire. Now we need to work out whether it's going to be going in a clockwise direction or an anti-clockwise direction. So using Lenz's law to determine whether the current flowed clockwise or anti-clockwise. So basically, it's going to be, now the magnetic field was increasing into the page, okay, because it's increasing. So magnetic field's increasing into the page. Therefore, the magnetic, so as, I'm just going to use shorthand. So as the magnetic field increased into the page, Therefore, magnetic field produced by the current must oppose this, and hence the magnetic field from the current is out of the page, Now, if the magnetic field is out of the page, use the right hand rule. So my fingers are coming out of the loop, like in the middle of the loop. So my magnetic field is coming out of the page, and hence if you line up your thumb, if my magnetic field is coming out of the page and we're using the right hand curl rule, therefore the current must be going in a anti-clockwise direction. So as B increased into the page, therefore as the magnetic field increased into the page, therefore the magnetic field produced by the current must oppose this, and hence the magnetic field from the current is out of the page. Therefore, the current must flow in an anti-clockwise direction. And then in brackets, that's because of the right hand curl rule. Now, I did quickly show you an electromagnetic braking video at some point. So basically, as we know with Faraday's law, a changing flux induces an EMF and then hence a current. Now, I showed you with electromagnetic braking, so I want you to watch this video. But basically, if we have a magnetic field set up and we have an iron block, an iron block whizzing past the magnetic field, what's going to happen is through this block, there is going to be a change in flux, because as it's moving past, it's going from no flux to some flux and then no flux again. So basically, as we know, a changing flux induces an EMF and hence a current. And these little swirls of current in a conductor are called eddy currents, and they're due to electromagnetic induction. And in a solid conductor, like a block like this, there's going to be little eddy currents in closed loops. So I want you to watch this magnetic braking video. So basically what's happening is, as the iron block, or whatever it is, the copper, aluminium, etc. Sorry, non-magnetic material. So copper, aluminium. If you bring that near a strong magnet and you whiz it past the magnet, it's going to induce an EMF because there's a changing flux through this aluminium block. And then it's going to induce an EMF and hence currents. And those currents are going to swirl in closed loops. And those closed loops are called eddy currents. That's what eddy currents are. So this is an example of a past exam question. So to detect vehicles, a rectangular conducting loop is embedded in a road surface. So on the road, there's a rectangular conducting loop. So varying the current in the loop produces a changing flux. Because we know if we have current, we also have a magnetic field. And if we vary the current, then we have a changing magnetic flux. And when a vehicle is above the loop, eddy currents are produced on the metal underside of the vehicle. So using Lenz's law, explain the production of the eddy currents. So basically, the changing magnetic flux on the metal underside. So the changing magnetic flux on the metal underside of the vehicle will induce an EMF and hence a current, which will result in swirls of current on the underside of the vehicle. and these swirls are called eddy currents. Now, the direction of these currents, you can work them out using Lenz's law. And Lenz's law, one more time to recap, Lenz's law states that the direction of the current created by the induced EMF opposes the change of magnetic flux that produced in the first place. So the magnetic field's going into the page to induce the EMF through the wire. Therefore, the current is producing a magnetic field that comes out of the page. And if you use your right-hand rule, out of the page would mean it's flowing in a anti-clockwise direction. So have a go at these questions, and we'll do some passing exam questions when I see you next. Cheers.